My name is Brooke Buddemeier. I'm a health physicist at Livermore National Laboratory, and for the past few years I've been supporting the Department of Homeland Security's nuclear counterterrorism and emergency response programs. And I'm going to go through some recent activities that the department has undertaken to improve emergency response planning around the detonation of an improvised nuclear device. This project came out of an activity that was funded by Congress, where our congressional members expressed concern that cities had little guidance available to better prepare their populations to respond to a nuclear detonation. The Department of Homeland Security took a three-pronged approach. One is they engaged the National Academies of Science Institute of Medicine to review the current medical response issues. That report is available at the National Academy's website. They engaged the Department of Energy National Laboratories, where I'm from, to help with modeling and develop key response planning factors. And they engaged the Homeland Security Institute to deal with communication and coming up with a communication strategy for response to nuclear detonation. So here's some actual language out of the congressional tasking. The Office of Health Affairs, that's in the Department of Homeland Security, shall set a strategy to ensure consistent and sufficient delivery of information to the public, medical community, and first responders on appropriate protective actions to prepare for and respond to a nuclear attack. So it sounds like it's all about communication, right? That's the big problem. Turns out when we started doing this, we didn't really have appropriate protective actions defined for a low-yield, ground-level nuclear detonation that might be from an improvised nuclear device. In fact, one of our responders at the workshop in the National Academy said it best: we don't know what perfect looks like. If we did everything right, we have no idea what that would look like. And it's no wonder. When you look at the guidance that's currently out there, for the basic question of should you run or should you hide, should you shelter or should you evacuate, you have two entirely different answers. RAND identifies evacuate immediately. DHS, take cover immediately. How can you prepare when we can't even come to consensus on what the right thing to do is? So to start this activity, we needed to understand where our perceptions were. What's in our mind when we think about nuclear detonation? And many of you may recognize this map from the Cold War. This is a strategic thermonuclear war map where there's hundreds of thermonuclear strikes on the U.S. All the shaded regions on that map represents radiation levels that could either get you sick or kill you. So, if we're walking into the IND planning with that kind of perception in our mind, it sort of throws everything out of alignment. When we look at an improvised nuclear device, a low-yield device like the 0.1, 1, and 10 KT devices that we were tasked to study, you can see that their ranges of effect are significantly different than the 1 and 10 megaton ranges that I've got on this graphic. We work very closely with state and local communities. In fact, LA was one of our key communities. We had several workshops worked with to try to better understand what are the key issues in response planning for a nuclear detonation. Some of the observations that I took away from those meetings are, state and local communities, few of them have any sort of regionally coordinated response plan for the aftermath of a nuclear detonation. There's a general lack of understanding of even what the response needs are. And uncertainty over the federal and state and local roles and responsibilities. I get two basic reactions. One is, nuke goes off, doesn't matter, we're all dead anyway. Walking towards the light. The other one is, that's a Fed thing, right? Nuclear weapons, we just put yellow tape around LA and wait for the feds to show up to solve our problems. Unfortunately, both of those kinds of gut reactions lead to a sense of apathy in planning that could get hundreds of thousands of people killed. Why? The critical actions are the ones that are taken the first few minutes and hours of the event. And the actions that you take then have the biggest impact on your safety and the safety of your public. Right now, those actions are not likely to be technically informed. In fact, the right answer may be counterintuitive. There was a distinct lack of scientific consensus on the appropriate actions. One of the things we started to do right away was work on that scientific consensus. We assembled a multi-agency, multi-organization panel, working group, to coordinate activities associated with modeling a nuclear detonation in a modern urban environment. We're never going to completely understand this event. We haven't been testing for a while, and even when we were testing, we never did, downtown testing. So actually knowing what exactly will happen is out of our reach, but we have the tools to better model what might happen, so we can provide better understanding to the responders and the medical personnel. The purpose of this working group was really to bound the uncertainty and identify what we don't know and the things that we do know, how they can help improve response. I'm going to give you a couple of examples, and actually they're kind of good news. If you look at the bottom graph, where you see all those red and yellow and blue areas, the bottom graph represents the elevated detonation point. That's sort of what we expected and what we typically model from our warfare days, the optimal height of burst detonation. This is actually the thermal radiation from the fireball impacting the city. The top image is one of a surface detonation. And you can see how the line of sight, as the thermal effects move through a city, how the buildings actually block a lot of that radiation. What we're seeing and what we're modeling is that effects like thermal effects are greatly contracted because they don't have the ability to get out of the urban environment and burn people at distances. Same thing for radiation. So this is prompt radiation. So this is the radiation that comes from the detonation itself. You can see that center top image. That's the gamma radiation. As you can see, it's streaming as the buildings block some of the field of view. Now, on the left side, you can also see the neutron radiation, which bounces around the environment and is less blocked. But overall, there's a contraction of the range of effects of prompt radiation. And that's important. We're also trying to model the effects of fallout radiation. That's the bottom image. You can see the fallout particles, and I'm going to go into this a little bit further in a minute, but the fallout particles land on rooftops and on streets, giving off that radiation. The red areas on the graph represent areas of hazardous levels of radiation. But you can see our modern buildings provide a lot of protection. The blue areas are areas where people who are inside buildings are relatively safe. Weather. So typically when you talk about nuclear effects modeling, you see a guy come up in a military uniform and he gives you these circles and cigars as the plume shape moves this way. We can do better now. We have a better understanding of what happens in the atmosphere when a detonation occurs and when the fireball rises and moves through the atmosphere. I'm going to give you 12 fallout patterns. This is Washington, D.C. I use that because the diamond of D.C. and the Beltway help provide a framework of range and reference. This is if we simulated a nuclear detonation on noon of the 15th of each month in 2006, using real weather from that time period. These are the kinds of fallout patterns you'd see. You'll note two things. One, there's a variety of direction that the fallout's going to go. Fallout doesn't go always in one direction. And there's also a variety of fallout patterns. A lot of us have this image in our mind of the cigar-shaped fallout pattern. That's because we used oversimplified modeling capabilities. Now, as we have the ability to do more complex weather and atmospheric modeling, you'll see that more of these patterns actually have structure to them. Something like this pattern, or that one's kind of Gaussian. That's like a butterfly wing. That's pretty pretty. The Nike swoop. So you can see how the variety of patterns, if you're always assuming a long, skinny, narrow pattern into your fallout, and that's how you base your response planning, you could really get yourself hurt. And so we needed to understand the variety of fallout before we went into launched our response planning activities. Since we did interact so much with LA, we did some very detailed modeling that I'm about to go through with you. Now, this is obviously notional information. I like the quote earlier, models are all wrong, but hopefully they're useful. What we're trying to get out of this information, this isn't exactly what's going to happen if a 10 KT goes off in LA, but hopefully the relative information that you can get out of it might help you understand how to better respond. So we're using downtown LA as our example. A 10 kiloton nuclear detonation gives off the light of 1,000 midday suns at a mile away. It's the equivalent of about 5,000 Oklahoma City truck bombs. We're using a workday population. We have detailed databases where we know 100 by 100 meters how many people are working in a city. We're using real weather from our weather database of July 15, 2006. The first thing to understand is that very bright flash of light is going to cause accidents. Blindness that may only last 15 seconds or a minute, not a big deal if you're standing on a street corner, but if you're driving 60 miles an hour down a freeway, it's a pretty big deal. So you can expect transportation issues, clogged roadways and arteries. Now, LA has a pretty specific city. It's got a very high-density downtown area, followed by a lot of urban sprawl. So when we're modeling a city like this, it's important to understand that the detonation effects, the primary effects, will knock down buildings within about 1,000 feet of the detonation. In LA, there's about 25,000 people within that circle. Out to about half a mile, there's about 145,000 people. That's an area of pretty severe effect. And what do I mean by severe effect? Well, this is a demonstration of a house in the Nevada desert. It's a slow motion image of a house that's been exposed to about the level of blast effect that we would see near the outer edge of that circle. Now, in this case, there wasn't any intervening buildings, so that bright flash of radiation and heat actually started the house burning at a mile away, even before the blast wave arrived. When the blast wave arrived, the positive pressure wave came through, knocked the house apart, and then very quickly, because a vacuum is created by the explosion, there's actually a negative pressure wave that moves the other way. So when you look at the image of something like this, and you think about, for example, when the World Trade Towers came down, all the dust and debris that was generated in that community, think, if your plan depends on you to run outside, look and see and know and do, you might want to rethink that, because there's just going to be dust and debris in the air. You won't know if it was a car bomb next door or a nuclear detonation a mile away. All right, moving out a little bit further, that blast wave will continue to propagate out several miles, and in fact, out to about 3 miles, glass is still being broken with enough force to cause injury. There's about 850,000 people within that circle workday population in LA. Now, not every one of them is going to be hurt. In fact, hopefully most of them won't be hurt. But it's important to understand the range of some of these effects, that it's not just a smoking crater and then everybody else is fine. It's much like an earthquake where you have this extended range of potential injury. And after this initial presentation, I have some details on potential injuries that you need to think about.
Now, large amounts of pulverized debris and molten earth are pulled up into the mushroom cloud.
I'll let Mr. Civil Defense talk about the rest.
This is where radioactive fallout is formed. The radioactive atoms produced in the explosion join with the particles of earth and debris. The mushroom-shaped cloud forms and climbs higher.
About 5 miles high for a 10 kiloton.
It now contains billions of highly radioactive particles of matter that we call fallout. The strong winds of the upper altitudes go to work on the cloud, blowing it off in one or more directions. Gravity tugs on the particles. The larger and heavier ones sink toward the ground, while the lighter particles continue to drift with the wind. Some of the lightest particles remain suspended in the upper atmosphere. As time passes, their radioactivity grows weaker, so that the longer they remain aloft, the less dangerous they are. But the heavier particles, spread by high-altitude winds, fall to the ground within 24 hours. Several miles from the explosion, they are about the size of table salt or fine sand. These are the most dangerous, because they carry the greatest number of radioactive atoms and so emit the largest amount of nuclear radiation.
So some key issues there. We're not talking about a cloud of noxious gas that's hanging in the air. This is a cloud that goes up high, particles the size of salt and sand fall out of it, cover the ground and other horizontal surfaces, and it's the radiation coming off those particles that's the hazard. It's not breathing it, it's not, being around the cloud, it's those particles that are giving off that radiation. When we look at the effects that of those prompt effects. That blue circle is my glass breakage range, got about, once again, 850,000 people within that circle, LA. The red marks on the screen are actually fire stations in that area. I call some of them out because I'm going to use them later in the presentation. This is the area where if you stood outside for the first day, you would get enough exposure from fallout to either make you sick or kill you. And you can see they've got overlapping areas, but also note there's a lot of areas, especially on the bottom of that image, where people could be hurt, especially from the blast effects, but they're not in a contaminated area. There's nothing stopping response activities from being conducted safely in that area and saving lives. All right, so one of the key issues that we get feedback on is stop giving us these, satellite view of the death and destruction. Tell us how this event is going to unfold and what I can do about it. So here's our example of an oblique view of what might be happening in downtown LA. First, you have that fireball shooting up. It's going to be shooting up at over 100 miles per hour up in the upper atmosphere. And you have that dust and debris generated from the blast wave down below. We've tried to turn that cloud of radioactive material into an image. In fact, it's often called the purple ping pong balls of death. This image is the cloud representing how the cloud moves through the atmosphere, and you'll see contours on the ground. So watch two things. Watch how the purple balls representing the cloud move, but also watch how the contours on the ground representing the radiation levels from the particles that have already fallen on the ground, how they change with time. This animation is going to go over about 6 hours. You'll notice in the upper atmosphere it flies off pretty quickly in two directions, to the east and to the north, and that's represented by the contamination levels that you can see on the ground. The different levels of contamination are represented in different colors. It doesn't really matter what they are, just to give you a feel for how contamination moves and changes with time. So that was the first hour, and now we're getting into hours 2, 3, 4, and 5. Bottom line, the cloud's gone after the first hour. It's a cloud. Clouds are going to move away. But there's material left on the ground providing exposure to the people. So you could walk outside after an hour, look up, blue sky, but the ground around you is pretty radioactive. Understanding that is a key response issue. All right. So here's the other factor we want to understand, is what does this mean to me? How will the event appear if I'm, say, standing on the Hollywood Hills? Well, we try to come up with some graphics to illustrate that. View from the Hollywood Hills. Once again, those little red dots there are fire stations. In fact, I'm going to pick on fire station number 6 here. Say those guys see a big mushroom cloud. That's not good. I'm going to bust out my radiation meter. So they bust out their radiation meter, start taking readings outside. That graph is going to show you the radiation levels that they're going to see with time. Just like the previous or earlier speakers, I don't want you to focus on the numbers. Just focus on the trend. And in fact, the one thing I want to point out is I think your limit is 10 R per hour for a no-go zone or turn back levels. 10 R per hour. So the scale on the left side of that graph goes up to 160 R per hour, just to put that into context. 15 minutes after the event, they look up, purple ping pong balls are going overhead, the radiation levels are starting to accumulate where they're at. Half an hour, it's over 150 R per hour. But look how fast it drops off. That's the silver lining of our fallout cloud. Fallout decays rapidly. You get over half of the exposure in the first hour. So here are some key factors about fallout that I want you to walk away with. One, it decays rapidly. That means two things. One, the bad stuff really occurs in the early minutes and hours of the event, and it's dropping off pretty quickly. Its dangerous levels of fallout are readily visible as it falls. It's not like this invisible death. Yeah, the radiation coming off of it's invisible, but the particles that generate hazardous, acutely dangerous levels of radiation, you'll see it as it comes down. It's not a respirable hazard. These particles are salt and sand-sized particles. They hit the ground, they lie there, they give off that penetrating radiation we're worried about. In fact, there's a little animation I've got here. Clunk, the particle goes down. What you're worried about is the rays of radiation coming off of it. And I've got another animation to show you what that means for a little cityscape. Particles coming down, landing on roofs, landing on the ground. And as you look at where the radiation is in the environment, you'll see it's near those horizontal surfaces. It's near those inadequate buildings which provide inadequate protection. Here's a cartoon that shows you the relative protection factors of various buildings. Now, the numbers there, protection factors, think of them like SPF of sunscreen. The higher the number, the better the protection. A wood frame house really only gives you a protection factor of 2 or 3. Not great, not horrible. If you have a shallow basement, though, you can get a protection factor of 10. Apartment buildings, other industrial brick and concrete buildings, can get you what we're calling adequate protection, which is protection factor of 10 or more. And if you can get into the heart of an office building, or a skyrise, or a residential building, those offer protection factors of 100 or more. All right, so let's talk about strategy. And in fact, do we have anybody from St. Vincent's here? Because I'm going to pick on them now. So we're looking at St. Vincent's. We're zooming in on that neighborhood. Typical LA neighborhood, you've got everything from your wood-framed houses, single-story houses, to a hospital. If you, for this particular scenario we're looking at, if you were outside, you would get 2,000 rem. Now, once again, I try and avoid numbers, so I'm just going to color code it for you. That's in the not a happy day category. So if you're outside, you can get, in the first 12 or 24 hours, you're going to get maybe 1 to 2,000 rem, certainly enough to kill you. If you jump into your wood frame house, it might provide you a protection of 2 or 3, not really enough to save you. But if you can get into a commercial structure, a brick or cement building, I'm looking, there's a church there. It looks pretty robust. It's probably got a protection factor of 10 or more. You're probably into the survivable range. And if you can get into that core of that hospital or in an underground parking garage, you could have no significant health effects from the exposure. In fact, if everybody in LA, and I'm just talking about fallout, we're going to take, these are only people that are more than a mile away from the detonation. If everybody in LA who was in the fallout area did the exact same thing, and that same thing was to run outside and stand there and make little fallout snowmen, you would have about 285,000 people that would get either sick, that's the yellow portion, or potentially fatal exposures in the red portion. Even if they went into a poor shelter, like a wood frame house, you would save 160,000 people from significant exposure. That's an inadequate shelter. If you can get them into what we're calling an adequate shelter, shallow basements, apartment buildings, cores of apartment buildings, commercial buildings with more than one story, you would save 240,000 people out of that 285 from significant exposure. And if you can get folks into the core of an office building or an underground parking garage, you'd have if everybody were able to get that, we'd have no significant exposures from this event, from the fallout. Okay? All right, so the next question I get. Now, Cold War guidance was you build your fallout shelter, you go there, 3 weeks later you emerge and rebuild society. I think we can do a little better. We need to understand how dynamic it is. Now, keep your eye on St. Vincent's. They're on the map right there. Right now they're in the red zone, unfortunately. Also keep your eye on the clock. These are how the radiation levels are changing with time. Right now it's at 15 minutes. It's growing, it's now at an hour. Look how quickly the dangerous levels of fallout are already shrinking. 3 hours, 4 hours. That's because radiation is decaying away. The material that deposited there is losing its energy. Now, there's always going to be a little bit left. It's the joy of radiation. There's always going to be some small fraction left. But at least you can see how quickly some of the initial hazards pass. So if you're sitting in your shelter, and in this case, let's use that church as an example, give it a protection factor of 10. That green line represents your dose if you were sitting in that shelter. This is the additional dose you would get if you knew which way to run, how to run out of that area. Or I should say, the dose you would get as you run out of that area. You can see in that first hour, trying to evacuate is a really bad idea. That's when you're going to get toasted by the high levels of radiation. But if you can spend at least a few minutes, hopefully half an hour, couple of hours in that shelter before trying to evacuate, you can certainly keep your doses a lot lower, possibly non-lethal. So in this particular case, we see there's actually a minimum dose. It's about 4 hours. For that particular type of shelter, for the length of time that they have to be inside and the distance they have to travel to leave the area, that's their optimal time. But as a health physicist, whether you left it 4 hours or 5 or 10 or 24, that's not as big of a deal to me as just don't leave it half an hour. Don't leave it 15 minutes. All right. Now, I wish we could say, and that applies to everybody in every place and every type of shelter. But the bottom line is, it depends on the type of shelter you're in. If you're in a poor shelter like that wood frame house, you might want to think about changing your location, because the best evacuation time for you is only about 30 minutes. The trade-off between the exposure you're getting inside that shelter versus what you would get while evacuating leans more towards evacuation. But still try to hang out for at least 30 minutes. Now, if you're in that hospital, St. Vincent's, and you're in the core of that hospital, or you're at the underground parking garage with a protection factor of 100, your optimum evacuation time is in days. That's because almost all of your exposure will come during your evacuation. And I think I already mentioned this, evacuation route is important. Somebody who is in a protection factor 10 building closer to the edge of the border might leave sooner than somebody that was further inside. Bottom line, stick it out for at least half an hour or an hour. If we compare your outside dose, say, regardless of what your strategy is, somebody in that building hanging out for a few hours might get an exposure of 100 rem. Being outside would be a lethal exposure. All right. And let's put this into perspective. So here's our areas of what I call acute effects, meaning there's glass flying around, there's buildings collapsing, so you've got a potential for actual physical injury. Or there's enough radiation from the fallout that could also be providing some type of physical immediate effects, sickness, acute radiation syndrome, or acute radiation sickness. That's the area of acute effects. That's that area over the county of LA. It's definitely a bad situation, but there's a lot of resources in LA to help manage something like this. Heck, compare that to the station fire. Station fire covered more area than the acute effects of the nuclear detonation. Now, that's not to say that there won't be contamination going all the way into Nevada, but this is the areas where you could have those kinds of immediate health concerns that you're primarily worried about, and where actions taken in the first few minutes and hours of the event could save lives. Public protection strategy, early adequate shelter. So if you suspect a nuclear detonation has occurred, get into a shelter. Shelter in place, a building like this isn't bad. It's single story, so it's not great. If there was a 2-story building nearby, I would probably move into that. Informed evacuation is another critical element to this, which means the response community must be prepared to try and identify the hazard areas and help inform the population so that they don't run into the fallout. There's going to be a lot of people running around trying to get to their families and deal with trying to avoid the situation. You can't necessarily tell, especially if you emerge from your shelter after half an hour, where the fallout is because it's already fallen. So identifying those hazards areas is critical, as well as identifying appropriate evacuation routes. First hour, that's when you need to know what to do before the event. Because if you're trying to look it up online after it occurs, it's not going to be a good situation. We're talking about hundreds of thousands of people. I know it's hard, but situational awareness, good communication, and independent responder action is critical to success.